In this video, we're going to be talking about how to use normal curves to predict how much data falls within a certain standard deviation of the mean. So in order to do this, we're going to talk about what's called the 68, 96, oh, that should be 95. Typo in my notes, 68, 95, 99.7 rule. So before we jump into it, let's just remember there are two important numbers that come with every normal curve. The first is the mean, and the mean represents the center of your data. And then there's also the standard deviation. And the standard deviation tells you like how much your data varies. One thing that you're going to see is we're going to use this little symbol, it kind of looks like an O, to talk about the standard deviation. Whoops, I can't spell standard deviation. So you'll see that throughout the notes here. So here's just some cool stuff, cool information about normal curves. First of all, I saw another typo. The first thing is that 68% of the data points fall within one standard deviation of the mean. That means that if you go to the mean and then go out one standard deviation, 68% of all of your data points are going to be in that range. Now, if you go out another standard deviation, so now you're 2 standard deviations to the left, 2 standard deviations to the right, 95% of all of your data falls within that range. And then if you take one more step out in each direction, so you're 3 standard deviations down and up, we're looking at 99.7% of the data. And you can see this depicted in this graphic below. It's a little blurry, sorry. But it just shows that as you get further away, the amount of data that you're going to have in those ranges is going to be smaller, right? So the closer you are to the center, to the mean, the more data you're going to have in that range. So this is a really useful rule because it's going to allow us to answer questions like, what percent of the time are you going to find someone that is between 5'7" and 5'8"? Or what percent of the time is your pizza going to be delivered within 15 and 20 minutes? And we'll talk about some examples of that, and we'll see some later on in this video. Before we move on, I wanted us to fill in a normal curve. So in this curve at the top, we have all these areas. We have 68% of the area, we have 95 and 99.7. And those are very symmetric numbers, meaning they go in both directions from the mean. What we want to talk about is what happens when you're just going like one standard deviation to the left or to the right. So let me show you what I'm talking about. So if you look at this normal curve down here in the purple at the bottom, this middle number is the mean. And then we've got plus 1 standard deviation to the right and then minus 1 standard deviation to the left. So we know that between these two kind of steps to the left and right, I've got 68% of my data. So that means that we're going to split that 68% equally between the left and the right side. So 34% of my data falls 1 standard deviation to the left of the mean, and 34% of my data falls 1 standard deviation to the right of my mean. So then let's look at the next step out. So let's say now I'm going to go out 2 standard deviations. So I know that 95% of my data falls within that range, that red range that we just looked at. Now we've already accounted for 68% of that data that's in the middle of my graph. So that means that we have 27% of my data left to fill in these 2 chunks right here. Now because the normal curve is always symmetric, we know that we're going to split that 27% exactly in half, which means that we're going to have 13.5% in this section and 13.5% in this section. Okay. So now let's take another step out. So we've looked at what happens when we step 1 standard deviation away, what happens when we step 2 standard deviations away. Now let's look at 3 standard deviations away from the mean. And our rule tells us that 99.7% of the data falls within that range. Now we've already accounted for 95% of that data. So that leaves 4.7% of the data to fall in these 2 chunks on the left and right. I'm going to split that 4.7% in half, so I have an equal amount on both sides. And that leaves me with 2.35%. Let me write this above the curve instead of 2.35% of your data in each of these chunks. So these numbers that we filled in, these are going to apply to all normal curves. So this graphic that we have filled in right here, you're going to want to use it for your homework as you're working through assignments, quizzes, tests, so that you can remember how much of your data falls into each of these sections. Now we are going to fill in one more piece of information, and that has to do with what's called the tails of the graph. So as we talked about, 99.7% of my data is falling within this 3 standard deviation range, which means that almost all of my data is represented already in the numbers that I put on the graph. But there's still a small portion that happens over here in the tails of the graph. Okay. And we know that since we already represented 99.7% of my data, I have 0.3% of my data that has to exist in the tails. And since I have 2 tails, one on each side, there's going to be 0.15% of data in each of these tails. So it's a very, very small percent of your data that's going to fall outside of that 3 standard deviation range of the mean. So maybe you want to talk about why we should care about any of this stuff. Let's do an example problem. And you're going to see why this graphic and why this rule about normal curves is so useful and so helpful. So in this example, we're going to be looking at one of the most common examples of normal distributions, which is distributions of standardized test scores. So one example of a standardized test score is the ACT. Most of you guys have probably already taken this or are planning on taking it soon. So here's some information about the ACT. The mean score was 21 in 2010, and the standard deviation was 5.2. Okay. So what we're going to do is we're just going to sketch a normal curve of this and just represent this scenario of the ACT. So the easiest part of this is that I know the shape of my graph is going to look like a normal curve. So I'm just going to draw a bell curve. Then I'm going to start filling in some information about it. So I know that at my peak, that's my mean, and that's going to be 21. And then what I want to do is I want to basically go out 1 standard deviation on either side. So I'm going to draw this dotted line so that we know we've got it lined up. If I go out 1 standard deviation to the right, that means I'm going 5.2 to the right. So 21 plus 5.2 is 26.2. And then if I go to the left, I'm going to do 21 minus 5.2. That's going to land me at 15.8. So that's just what happens when I go 1 standard deviation out from the mean. And what I'm going to do is I'm actually going to take, we'll do it at the end. Never mind. Let's fill in the rest of our standard deviations. Let's say I want to go another standard deviation to the right. I'm going to take that 26.2 and I'm going to add another standard deviation of 5.2 to land me at 31.4. Maybe we'll just add the other one while we're here too. If I go another standard deviation up, it's going to land me at 36.6. Okay. Now, if you know anything about the ACT, you know that the max score you can get is a 36. So we're going to look at this number 36.6. And we know that no one can actually ever score 36.6. This is an important thing to know about normal curves. They are just approximating our data set. They're never a perfect match. There's never a model or representation that we could give that's going to be a perfect exact match to the scenario. But what happens is that these models are useful for our purposes. So there was some famous mathematician that said, no model is perfect, but some are useful. That's exactly what the normal curve is. It's not perfect. Like here, when I go 3 standard deviations up, I get a score that's not even possible on the ACT. But this model is still useful to talk about the ACT. in the ACT scores. All right, let's go ahead and fill in the left side of my graph. I need to go down another standard deviation, which lands me at 10.6. Then if I go down one more, you get a 5.4. Okay, so let's just remember really fast what all these numbers represent. So these numbers along the bottom, these are ACT scores. And then the height of my graph at each of these scores represents how likely it is to score that. So at 21, that's where my graph is the highest. That's the most likely score to get on your ACT. And then the further away you get from 21, the less likely it's going to be that you get that score. So let's go ahead and take a second and fill in these percents that we copied in this graphic above. And we're just going to use them to fill in this chunk of or this representation of the ACT scores. So I'm just going to go ahead and put these numbers in here. 34%, 13.5%, 2.35%, and then my tail is 0.15%. And again, the reason I'm just copying these down so quickly is because this is the normal curve model. No matter what your situation is, no matter what your scenario is, these numbers are always going to be the same because of that rule that we talked about at the very beginning. So let's go ahead and answer some questions using our curve that we just created. So what percent of students score below a 21%? So in this case, I want to know below 21%, how many students live over in this category over here that I'm highlighting in yellow? Okay, and that's going to be, there's kind of several different ways you can think about this. One, you can just add up all of those percents that we have here. 34 plus 13.5 plus 2.35 plus 0.15. And what you're going to get is you're going to get 50%. This one you can actually do without adding everything up because 21 is the mean. And if 21 is the mean, it means it divides our data exactly in half. So 50% of the data is going to be below 21, and 50% of the data is going to be above 21. All right, let's go ahead and take a look at the next problem. What percent of the students scored above a 26 on the ACT? Now, if you look at your scores along the bottom, you've got a bunch of decimals, right? 26.2, 31.4. So here we don't have exactly 26. So this is, again, where the model is going to be useful, even though it's not perfect. We are going to look at everyone who's above the 26.2 score. Okay, we're just going to assume that 26.2 is pretty close to 26, and we can use our model to give us some information about that. So to figure out how many people scored above 26, I'm going to add up all the percents. Oops, I'm going to do this in black. All the percents of people that fall in that category. And when I do, I'm going to get 16%. So that's the number of people that score higher than a 26, or that in 2010, when this data was gathered, scored higher than a 26. All right, let's take a look at the next one. If you're feeling pretty confident about this, hit pause, fill in, answer the next couple questions on your own, and then come back and check your answers. Okay, about what percent of students scored above 16? Now this about is an important word, because again, on our model that we have above, there's not a 16, but there is a 15.8, and that's about 16. So we're going to count everyone that scored above a 16%. So we're counting all of these people that got 16 and anything higher than that. So again, to figure this out, I'm just going to add up all these percents. 34 plus 34 plus 13.5 plus 2.35 plus 0.15. And what I should get is an 84%. So 84% of students scored above a 16. Okay, in our next one, we're looking at about what percent of students scored between an 11 and a 26. So I'm going to find on my x-axis of my graph Where's 11? Well, 10.6 is about 11, so that's kind of my starting place. And I want to go all the way until I hit 26. So how many kids are between 11 and 26? It looks like it's just that chunk right there. Those that are between 10.6 and 26.2 on our normal curve up there. So I'm going to go ahead and add up all those percents. And when I do, I get 81.5%. So that's the percent of students who scored between 11 and 26. And that's a pretty sizable chunk. Most of my students are falling into that category. All right. Let's take a look at this last question. So the last question is going to make us think a little bit harder. So your friend Calvin would like to go to a very selective college that only admits the top 1% of all student applicants. Calvin has good grades and scored 33 on the test. Do you think that Calvin's ACT score gives him a good chance of being admitted? Explain your answer. Now here's an important thing to note on this. As with many statistical questions, there's not going to be like a hard and fast answer to this. Okay, so we're going to be doing some justifying and some reasoning about this. What I'm going to do first is I'm going to plot Calvin's score on my graph. So 33 falls somewhere between 31.4 and 36. Maybe it's going to be right here. I'm going to draw that line all the way down. So this green line, that's going to be 33. That's Calvin's score. So what we want to figure out is Calvin's score part of the top 1% of all the student applicants? There's a couple different pieces of information we can look at here. First of all, we can think about the percents that we know, like from 31.4 on, we've got 2.5% of the data falling in that chunk. So our question is at least 1.5% of the data falling in this first section? And this is a really good question, and I don't know that I could tell you if there's like a right or wrong answer to this. I would say that Calvin, if I was answering this question, I would say Calvin has a pretty good chance of getting in. If he's not in the top 1%, he is really close to the top 1% of the data, right? He's definitely in the top 2.5%. That's an easy one. And he's also kind of like halfway through this 2.35% chunk, which means that I would guess that he is in the top at least 1.5% of his class, or of everyone that's applying to that college. Okay. So number 6, this is the kind of question that we really, really care about. Okay, it's kind of hard because there's not like an answer to this question until he either gets admitted to the college or he doesn't. But we're able to use this model of the normal distribution of ACT scores to really help us to understand and to answer a question that we don't know the answer to, but we can predict the outcome. Is Calvin going to be accepted to this college or not?